Hello everyone, welcome to the technical overview of my Chameleon Skin system that I've been working on in Unreal Engine 5. This isn't going to be a step-by-step tutorial on how to create absolutely everything in this project, it's just going to be a guided tour of the main bits so that you can, if you're curious about how it works, it explains how it works, and if you are a reasonably intermediate user of Unreal or doesn't have to be Unreal really, could be any engine, reasonably technical person, then it should be enough information to recreate for yourself or steal the bits that work for you and adapt into something. So if you haven't watched the previous videos, the Chameleon Skin system is essentially this, where if I press a button right here, the character will paint themselves to look like the background. So this isn't transparency, they are actually painted with these textures, so as soon as I move the camera, you can kind of see that it doesn't adapt to match the perspective. And I added an alternate mode that swirls the colors up a bit to form a camouflage pattern. So this is more of like a kind of, it takes the colors from the background and mixes them together rather than using trying to create like a one-to-one image. So if we want to go into how this works, I've put the important things all in just this one folder here. There is the Camo blend with noise underscore material, which is the main material that is applied to the character during this. And there's the unwrap screen space material, which is pretty important as well. We won't get into those just yet. We'll actually go and look at the character. So this character is the BP camo character. It started life as a duplicate of the standard Unreal third-person character. And what we have that is new is there are two scene capture components here. There is the scene capture unwrap, the scene capture world. The scene capture world has pretty standard settings for a scene capture. It's set to render the scene primitives, which means it will capture an image of the scene itself. And other than that, the main thing that's different is it has a bunch of stuff turned off. So bloom, eye adaptation, a bunch of lighting stuff, a bunch of post-processing stuff. Essentially, most of the stuff that is turned off is because we're going to be using the scene capture to paint the character, and we don't want to apply any of these twice because they will be applied to the character itself. So if you are standing in shadow and you paint yourself shadow colored, then the shadow will apply to the shallow colored skin and you will be twice as dark as you should be, which isn't ideal for camouflage. The scene capture unwrap renders even less things because it only is going to be rendering the character and nothing else. So it uses a show only list and it has most things disabled, and that's about it from here. So we dive into the event graph. There's some important setup in here in begin play. So we've got some basic like caching of local variables, adding input mapping. We don't really need to worry about that now. It's some fairly standard stuff. But the main meat of the begin play that we'll be interested in is setting up the scene capture components and the render targets that we're rendering to. So this will be the first things first. We have a debug option here that if it's false, we're not going to be doing what comes next, but it will generally be false. And that is that we are hiding the character itself from the world capture component. So there is a debug mode where they will still render in it. That's just for testing things like camera positioning and that sort of thing. But in the general case, the world capture component doesn't render the capture itself, doesn't render the world capture component, doesn't render the character itself, and hopefully the reasons for that are pretty obvious because you don't want to be painting yourself as yourself. And the unwrap capture component only shows the character mesh, so we need to add that to its list. We'll be using this camo blend with material, but we need a dynamic instance of it because we'll be messing with its parameters, and if there's multiple instances of this character, they don't all need the same parameters. We'll cache that off for later. And before we've done any captures, we do just have a starting color that we'll be setting up as the base character look. After that, there is a bunch of render targets to create. So for now, we have 4. We have 2 unwraps, 2 world captures, and the reason we have 2 is that there are 2 different ways the character sorry, not 2 different ways. There's 2 the character will blend between 2 different camouflage patterns, the current one and the one that you have just blended to. So for that, we need to kind of double buffer things up. There is a bit of there's an opportunity to optimize here, but I won't be getting into optimization for this video. But we might not need all of these if you were being absolutely optimal about it. There's ways to get rid of them. So the height of this, the size of these render targets is defined by the height and the aspect ratio, which I've set at 0.5. And the exact height in pixels is different if the character is player controlled or not. So if the character is player controlled, we have a bigger texture, so it'll look better, be a little bit less pixelated. Whereas NPCs will be under a lot less scrutiny, so we can get away with cheaper textures for them. And to explain a bit of what these do, the unwrap will be used to store a UV unwrap of the character. If you don't understand what that means, I'll get to it. Whereas the world render targets will be used to store the image of the world. And those are the 2 things we'll be using to build our camouflage pattern up from. And then we've got some final bits. We've randomized some noise, not important for now. Update and apply the material. That just pushes all the parameters we need to for the camo material to render itself into the material and applies it to the character. Again, we'll come back to that later. And then the other thing is just altering the field of view of the scene captures to account for the aspect ratio. This is basically because the field of view as set in the properties is the horizontal field of view. I basically want it to be the vertical field of view, and because we've got a slightly skewed aspect ratio, that needs to be accounted for. Oh yeah, and the reason we use a portrait layout for these is because the character is just simply taller than they are wide. So and the effect looks better the more of the screen the character fills. So doing a square or a widescreen layout wastes like a whole lot of screen real estate for these render captures. And what I changed, but let's recompile. And so if we move on to like where the heavy lifting is done, this refresh camo function is called when I press the button. The first thing it does is set the capture transforms. This is, if we go back to the viewport, you'll notice these are just at the origin of the character. That's because when we call set capture transforms, they will be moved to be in the location of the camera if it's the player, or if it's an NPC, it'll be moved to the location of the player's camera. So that's why they're not locked to the follow camera itself. They are free floating because they need to move to they might need to move to the position that is someone else's camera. And then if we go through here, this is debug stuff, ignore it, but it's basically setting a material for debug rendering, which will then be removed immediately afterwards. First things first, we set the target. We set the render targets for the captures, and this is where because we have 2 sets of render targets, we're going to be overwriting number 2 if we have a source and we have a target. If the source is currently number 1, then we're going to be overwriting number 2. If the source is currently number 2, then we're going to be overwriting number 1. Because one of these is the one that we are currently displaying, and one of these is the one that we're going to be blending to in a moment. Once we've done that, we capture a picture of the world, and then we set the material on the character to this special unwrap screen space material, and we capture an image of the character using the unwrap capture. Then we're going to update and apply the camo material, which will push all of the parameters into the camo material, and those parameters include which render targets to use. It's a bit messy with all this whole like we have to swap it around based on what the current source is. That's something that definitely I would clean up if I was going to put it in an actual game. Well, I won't get into like the best ways to clean this up now, but I definitely have some ideas. So yeah, we've gotten these two captures, and then calling this is pushing them to the material, because then Jeremy needs both of them. Then we flip around. This source is one ball, so we'll use the other set of render targets next time. And then update the HUD, which does some debug stuff. So the best place to go from here is this unwrap screen space material. So essentially what we have here is, as you can see in the viewport, we have you can kind of see just behind the rest of this vertex soup. It should be unlit. 1 second. The normal Quinn mesh, which is the female mannequin that comes with Unreal 5, and half of her is rendered kind of strangely. That's because in the preview window, she has 2 material slots. The preview window only applies it to 1. I haven't found a way to get it to apply it to both. But yeah, what we're basically doing is taking the text coordinate, and this might seem familiar to you if you've seen some of the ways people do like damage effects or other things like that in Unreal. It's a pretty common trick, but you take the texture coordinate, which would be the UV, and you convert it to the screen coordinate, and then you just plop it in front of the camera on the near clip plane. That's what this code is doing. I've done it. You could do this with nodes. I've chosen to do it with code just because there's a bit of like flipping around, and because we take a UV, we have to convert it to a screen coordinate, because UVs are 0, 0 to 1, 1, whereas the screen coordinates are 0, 0 in the center to 1, 1 in like the top right, and -1, 1. -1, -1 in like the bottom left, and so on. Yeah, so that's essentially what all this is doing. And then because the world position fed in here is an offset, not an absolute position, we need to subtract the absolute position to make this the correct offset. So essentially we've rendered the character using this material, and instead of the vertexes going where they should be in like 3D space, they've been splattered in front of the camera and created a UV unwrap. So if we save this out, we could then render the character with this, and they would appear in these colors. So at this point, I should probably just demonstrate in game what that kind of looks like. So if I toggle my debug HUD here, I run over here, press Q. That's not working for some reason. Is that not working? Alright, so I fixed that. It took me longer than it should have to find out what went wrong, but you know, that's the dangers of demonstrating these things live. Sometimes you will screw something up. Anyway, got it working again. So as you can see here, we have the unwrap texture in the bottom right. And yeah, it's basically just a copy of the character's UVs printed out in a new way. And you may also notice that the color of them changes as I move the camera around. So there's a reason for that, and that's because we are, let's put this back and unlit, we are, instead of feeding the normal color into the base color over here, we're actually feeding the original screen position of the pixels. So instead of just using the screen position node, we have to recalculate these from the absolute world position, excluding material offsets, and that's because at this point we're working with colors. This stage of the material uses the pixel shader, not the vertex shader, so this world offset has already been applied. So this screen position would just return the UV. We don't want the UV, we want the actual screen position of the character. So we're then taking that, and ignore this bit for now. That's an edge case fixer. We're taking that and we're just printing it into the color. We're also just, so the R value is the X coordinate and the G value is the Y coordinate, which is why when the character is closer to the top of the screen they become red, because the green value, as in Y, is becoming 0, and they become more green when they're at the bottom of the screen because it's becoming 1, and more green if we go to the left and more orange if we go to the right. So yeah, that's what we're feeding in here, and like I say, we'll come back to this later, but you could just pipe this directly in and it would still work pretty well. And the next thing to look at is the Camo blend with noise material, which is where everything is combined basically. So it's a pretty bare bones texture, pretty bare bones material. All I've set up is we use the basic normal and the basic tangent. That this will be whatever is set up on the mesh normals. So there's no normal mapping or bump mapping or anything like that. No metallic, no specular, max roughness, no anisotropy, no ambient occlusion. Just, you know, keep everything very simple so that the colors are represented accurately. And as that, you can see there's two parts of the graph that look very similar, and these are what are feeding into the base color. So each of those is a texture pattern. One of this will be the source, this will be the target. We're blending from the source to the target using this time blend here. Now this is something that could definitely be optimized, because we have just two exact copies of the same logic. This should really be moved into a material function, but I've left it as it is just to make things easier while prototyping. So how it works is that we're taking the unwrapped texture that we've just generated and sampling it. Oh, by the way, the reason this appears here, even though they're meant to be dynamic render targets, is because I do have some ones saved out just to make it easy to debug these. So we're taking our source unwrap, which will look something like this. We're reading the red and the green values, which are the X and the Y coordinates of their original screen position. We're adding some noise, which we'll ignore for now. And then we are using those X and Y coordinates as the UVs to pass into this sample of the scene capture. So here we have, it's easier if I actually take the noise off, which should update. So yeah, essentially we've already gotten the real screen position yeah, we're getting the real screen position of these pixels if we hadn't unwrapped them, and we're using that to look up the location in here, which then gives us a texture that looks something like this. So you could imagine it as there is a character shaped cutout in this image, and the pixels are being mapped onto here. And that's basically all there is to it. So we're doing the same thing with the target, which, as I mentioned, it's kind of unnecessary to just have all the same nodes copy pasted, but here we are. And yeah, we just lerp between them over time. So that's basically how it works. I'll just show you one more time with the things open. Create a queue. We are taking the turn the noise down so you can see it more accurately. But yeah, you can essentially think of it as like if you just we're rendering the character as if it had that bottom material applied to it, but then we're swapping out all of the colors by looking up the converting the pixel's color into UV coordinates and looking up a new color from the top image, the world capture. So real quick, one thing I forgot to mention that's pretty important is that if you're using a mesh that has any UV symmetry, I think that's the proper term. I don't actually know. I'm not a character artist. This system won't work. So to explain what I mean, here's the default mannequin. If I click on his legs, you'll see that each leg is mirrored in the UV. It uses the same area of the same texture, and it's the same for the arms, which makes perfect sense if you are not doing what we're doing, because it keeps the texture size down. But you need to use a mesh that does not do that with this system. And if you don't have a mesh that does that already, say if you're just working through this from third person default, you can create one quite easily by duplicating the starting mesh. Save that real quick, and then you can open it in the UV editor, select every face, click the unwrap option and give it a second, and then boom, this is none of the faces should be shared now. And obviously this has completely scrambled the textures on the default mesh. Like, it won't work with its base textures anymore. It would be completely wrong. But we don't really care about that for our purposes. So apply that. So yeah, if we go in here, it looks like that, and the default one is still like that. So it's important to use this one in your Camo system, or any mesh off the store that satisfies that requirement of not duplicating up areas, because otherwise what you'll get is both arms will be forced to be the same color. So obviously that's not going to work with this Camo system. So that's how it works, and I'll go and backtrack and explain a few of the things I skipped over. So the first of those is noise. Once we've got the new coordinate, once we've got the coordinate that we want to look up in the world capture, we apply an offset that is purely random to that coordinate, and we scale it by the scale, and then we feed it into a Perlin noise function, and that will give us an offset value basically, and then we're scaling that offset value by the magnitude and applying it, adding it back to the original coordinate. So essentially, it's like for every pixel in here, there will be a slightly different like pseudo-random offset that we're getting from the noise function that will essentially kind of like swirl and distort the image around. So the scale could be thought of as the zoom of the noise. Like the higher the noise, the higher the scale, the more the noise will repeat, the more granular it will look. Whereas the magnitude is how much impact the noise has. Because all of these values will be pumping out something between -1 and 1, I believe. Yeah. In each of their components. So a noise value of 0.2 means that we're going to move, the noise is going to move each coordinate a maximum of 20% of the screen, or 20% of this world capture here. If you set the noise to 0, then obviously the noise has no effect. And if you set the noise much higher, then it can potentially swirl around the image a lot more. Yeah, and that's how noise works. So if you have higher noise, you will, yeah, just take the layout up. If you have a higher noise, then you will have a higher, you have more, a more swirled up kind of pattern. It will stop resembling like a perfect capture of an image, and it will more resemble camouflage that just uses the colors of what was behind you. The other thing to backtrack on that I skipped over was this edge case fix for faces that are parallel to the camera. And the best way to explain this is actually with a cube instead of with the with a character model. So yeah, if you don't know what a normal is in 3D rendering, it's essentially you could think of it as the direction pointing out of a face towards the outside world. That's the simplest way I can explain it, really. So if we have a cube here, it's facing the camera, it's transparent so you can see all of the faces at once. And there would be a face, there's a face on the right here, its normal is pointing that way. There's a face on the left here, its normal is pointing that way. There's a face on the top here, its normal is pointing that way. Face on the bottom, normal is pointing that way. There's a face pointing towards us that has a normal that's just a dot pointing directly towards us, and there's a face pointing away from us that is also, you know, pointing directly away from us. So it wouldn't be an arrow, it's like we'd be kind of invisible from this perspective. So if we think about like the areas that we would, if we were using our camo tech with this cube instead of with a character model, when we capture the front face, we'll be using this as its reference area to look up colors, so it would have this checkerboard pattern applied to it. It'd almost look like a window. The face on the other side of the cube would be doing something similar, but it's capturing a smaller area because of the perspective shift. It's slightly smaller from the camera's perspective because it's further away. So if we actually rotated the capture around, we would, if we rotated the cube around, it would end up being the back face would actually have a slightly bigger pattern on it. But that's probably fine. It's not too bad. These side faces are where we get issues, because if we capture from this perspective and then rotate the cube, everything is kind of stretched out like this. We don't have a checkerboard pattern anymore, we just have like this very odd looking thing. It's like obviously an error. So how do we fix this? There's probably a bunch of different things you could do, but the solution I have gone for is this. We take the normal of the pixels, because we're working pixels here because we're at the color stage. We take the normal of the pixels into account, and we slide the coordinate back along the normal from its like screen space perspective. So we take the pixel normal, transform it to view space. We only want the X and the Y, so the R and the G, because materials always work with colors. And we apply quite a strong exponent to it. So because we're ignoring the Z value, if the normal is pointing directly towards or away from the camera, the Z value will be the majority of the normal, and the X and the Y value will be very low, like probably below 0.5. When you do like 0.4 to the power of 9, it's going to get slammed down to pretty much 0. So this strong exponent kind of just makes sure that only faces that are parallel to the camera have this offset applied, and ones that are facing the camera or facing away from the camera have very little of this offset or none at all. So yeah, we take that, and yeah, this will never be above 1 because normals are normalized. So the maximum any of these components would be 1. So we take that, we multiply it by this magic number here, which is a negative magic number, and that's how we make it slide backwards along. So if you think about how this would work with the cube, it would be very strange, because the normal would be fine until you reach this edge. Then all of a sudden the normal changes, and we start applying this offset, and the offset would say, oh, well, sample like this region instead. But we're not actually working with a cube, we're working with a character mesh, which most of its limbs and whatnot have more in common with cylinders and spheres. So the normal would actually gradually change as you went around a corner, and the offset would gradually change. So you would end up having something more like you sample this region or something as it slowly increases as you go around the corner, and you get something a bit more like, it ends up looking a bit more like the other faces. So to illustrate how that looks in game, let's turn the noise off. So we go up to this wall here. So you can see all of the stuff facing us just looks like it's copied what's behind it. But as we rotate around, we start to see a little bit of weirdness, but no massive stretching. So like the panel on the chest there kind of starts to break the pattern, and that's because it's sort of doubling back on itself, or like on the left leg from our perspective. So the texture sort of like starts to double back on itself as it gets to like a parallel face, and then eventually you'll get like a kind of mirrored seam. It doesn't look perfect, but I think it looks a lot better than the alternative, which if you go back to the first video I made on this tech, it was like as soon as you rotated the character, it was horribly stretched on every face that wasn't facing the camera. Yeah, so that's the other thing that's the thing that I needed to backtrack on, and that's essentially all of the system. There's a few other things like that we could go into, but most of it is the sort of thing you could kind of work out for yourself, and it's fairly boilerplate, Unreal-y stuff. There's these big functions here, like update and apply camera material. All it's doing is pushing all of the parameters into the camera material. So because you may have noticed in the material, it always blends from a source to a target. So because we've got 2 different sets of render targets, when we apply a new camera pattern, we actually have to swap those render targets around. So tell it that the source is the if it was previously at like the source is 1 and the target is 2, then we have to tell it that the source is 2 and the target is 1, and so on. And then pass in all the noise parameters for each pattern needs its own noise parameters. All of this is definitely like very good candidate for optimizing away some stuff. But for now, yeah, it does use speak inefficient. Like, if it's this, use this. If it's that, use that. You could probably compress all of this into like a struct or something, make it a lot cleaner. Yeah, and then this is also where the transition time is applied. So we apply the material can tell what like the global time is. So if we just pass it a start time and an end time, then it can work out at what point between the two Camo materials it should be blended to. And the noise is slightly randomized every time you apply. So the magnitude is whatever you set it to, but it does get an additional 10% added on or taken away. The same goes for the scale. And then the noise offset is a completely random unit vector each time. If we go back here, if you remember, then this is where we apply that noise offset. So within a noise pattern, this kind of just means we're at a different point in the noise pattern. It means we should get a very different set of offsets. And yeah, that's pretty much everything. So hopefully this has been somewhat informative, and I haven't forgotten to miss out anything important. But yeah, if you have any questions, leave a comment or something like that, and I'll try and answer them. But this is probably the last video I'll make on this for a while, because I'm about to become pretty busy with other stuff. Cool. Alright, see ya.